So let's talk about quantum computing. It's this mind-bending idea that uses the weird, counterintuitive rules of quantum mechanics to build computers that can solve problems that are flat out impossible for even the biggest supercomputers we have today. And yeah, it really does promise to change just about everything. Let's get into it. You know, to really get why quantum computing is such a massive deal, we gotta look back for a second. For the last half-century, pretty much our entire modern world has been built on the back of one single, incredibly reliable rule. And that rule is Moore's Law. It's this observation from way back in 1965 that the amount of stuff we can cram onto a computer chip, the number of transistors, basically doubles every 2 years. This incredible, relentless pace is the engine that powered everything. It's the reason the phone in your hand is astronomically more powerful than the computers that got us to the moon. But here's the thing. That ride is slowing down. We're hitting a wall, a literal, physical wall. See, we've gotten so good at shrinking transistors that they're now just a handful of atoms across. And at that tiny scale, the normal laws of physics start to get weird. Electrons start doing things they shouldn't, like teleporting through barriers. The very quantum weirdness we tried to avoid is now getting in the way. So, what if we just flipped the script? What if this problem wasn't a problem at all, but actually this solution? Instead of fighting these quantum effects, what if we built a computer that harnessed them? That right there is the big idea behind quantum computing. It's not just a faster version of what we have, it is a fundamentally new kind of machine. This chart gives you a really clean breakdown of the key differences, but pay close attention to that last line, sequential versus parallel processing. Here's an easy way to think about it. If you're looking for one sentence in a giant library, a classical computer reads every book one after the other. A quantum computer, in a way, gets to read all the books at the exact same time. Okay, so how on earth does it do that? How can it look at everything at once? Well, it all comes down to the magic ingredient, the heart of the quantum computer, something called a qubit. Let's break down what this thing actually is. First, let's just quickly remember our good old classical bit. It's super simple. Think of it like a light switch. It's either off, which is a 0, or it's on, which is a 1. End of story. There's no in between. Now meet the quantum bit, or qubit. Forget this simple light switch. Imagine a dimmer switch. It can be all the way off, that's a 0. It can be all the way on, that's a 1. But it can also be somewhere in the middle, a blend of both on and off at the same time. This ability to exist in a combination of states is the superpower we call superposition. So this both-at-once idea is superposition. And I know you might see an equation and your eyes glaze over, but don't worry about the math. All that's really saying is that the qubit is in a mix of 0 and 1. Those Greek letters just represent the probability, the chances that when we finally measure it, it'll pick a side and land on 0 or 1. This sphere is a perfect way to picture the difference. A classical bit can only be at the very top, the North Pole, or the very bottom, the South Pole. 2 spots, that's it. A qubit, on the other hand, can exist as any point on the entire surface of that globe. Just think of how much more information you can encode with that. Okay, so having these powerful qubits is one thing, but a pile of them isn't a computer, right? We need to actually control them and make them do useful work. That is where quantum gates come in. In any kind of computer, gates are the verbs, they're the action words, they're the tools that actually manipulate the information. They're what lets us flip, rotate, or link our bits, or in this case our qubits, together to actually run a calculation. So a classical NOT gate is easy peasy. It sees a 0, it flips it to a 1. Sees a 1, flips it to a 0. But a quantum gate, like this Hadamard gate, does something that feels like magic. It can take a qubit that is definitely 100% a 0 and in one step put it into a perfect 50-50 superposition of being both 0 and 1. It literally creates uncertainty from certainty. And it gets even more powerful when we get qubits to work together. This is a CNOT, or controlled NOT gate. This is a 2-qubit operation where one qubit gets to be the boss of the other one. And when you link qubits like this, you can create another famous quantum phenomenon called entanglement. This little table shows you exactly how it works, and the logic is actually really simple. Just look at the first 2 lines. If the control qubit A is 0, nothing happens to the other qubit. It's left alone. But, and here's the cool part, if that control qubit A is a 1, It reaches over and flips the state of the target qubit B. It's this simple if-then logic that lets us build really complex quantum algorithms. All right, let's step back. We've got qubits that can be multiple things at once. We've got gates to control them and link them up. So what? Why do we care? Well, this is where it all comes together. This is what unlocks the potential to solve problems that are just completely out of our league right now. Let's make this really concrete. Imagine a classical computer with 4 bits of memory. At any single moment, it can store exactly one number. For instance, out of 16 possible combinations, it could be storing the number 4. Just one. But a computer with 4 times qubits? Thanks to superposition, it's not just holding one number. It's holding all 16 of those numbers simultaneously. Not one after another. All of them at the exact same time. It's like having 16 classical computers working in parallel for you. And here is the absolute key. This power grows exponentially. Every time you add just one more qubit, you double the computer's processing space. It goes from 16 to 32, then 64, then 128. You very quickly get to a number of parallel states so vast that a classical computer could never, ever hope to match it. This incredible parallelism is what makes quantum computers perfect for a special class of problems. We're talking about things like designing new drugs by simulating molecules with perfect accuracy, something that, for certain molecules, would take the fastest supercomputer we have longer than the age of the universe to figure out. No joke. And that brings us right back to the beginning. We started by talking about classical computers hitting a physical wall. But by embracing the strange, powerful rules of the quantum world, we're not just breaking through that wall. We're opening up a whole new universe of possibilities. So I'll leave you with this question to chew on. If we had a machine that could explore every single potential answer to a problem all at once, what currently impossible challenges would we finally be able to solve?